Hi, this is our ME110 tolerance scenario project. We did our project on an SSD enclosure. And for our group, we have Kevin, Wilson, Ji, and Alexander. So starting off with what our SSD enclosure looks like. So this is what our SSD enclosure looks like. And what it is that it's essentially a protective casing that goes around an external SSD to protect it from any damage. So moving on into our assembly drawing. So this is our assembly drawing, and as you can see, there are 5 distinct parts of our assembly. So the first is an outer shell that's made out of aluminum, and the second is a toggle plate, the third is a push button cap, the fourth is an enclosure latch, and the fifth is a storage compartment. And so our outer shell is made out of aluminum, while every other part of the assembly is made out of ABS plastic. So moving on into the drawing for our storage compartment. So this is our drawing for the storage compartment, aka the outer shell. And you can kind of see in the drawing that we've used a couple of GD&T features. So first is a perpendicularity GD&T symbol here, as well as a flatness for the top of the outer shell. In addition, as you can see in this detail on the left here, we're using a surface profile GD&T, as well as a true position GD&T.
Alexander Kim, and this is the storage compartment. Shown here is the storage compartment, the portion of the assembly that houses the SSD itself and slides inside of the outer shell to protect the SSD. Along with housing the SSD and sliding into the outer shell, this inner housing compartment also has all of the other components attached to it when assembled. Because of this being a crucial component for assembly of all the components, GD&T is necessary to get proper functionality, allowing for a functional fit, clearance, and alignment of all the components. Therefore, we set datums A, B, and C accordingly and applied the following. For the bottom surface/wall of the enclosure, we applied parallelism with respect to the C datum with a tolerance of 0.01 inches. This ensures that the enclosure will be parallel with the inside of the outer shell as well, and will not lead to any clearance issues or binding when trying to slide it in. Next is a true position feature with a tolerance of 0.01 inches with respect to the A and B datums, applied to the 2 inner assembly holes in the enclosure. This ensures proper alignment of the holes for the mating of the parts when assembled. Finally, there is a surface profile callout with a tolerance of 0.04 inches with respect to the A, B, and C datums. This gives the allowable amount of variance in the profile and contouring of the part that will still allow it to function with proper fits.
Large toggle plate. So the purpose of a large toggle plate is to serve as the interface between the push button cap and the latch itself. So we have datums placed at A, B, and C to ensure that everything slides properly without interference. So the first tolerance feature is we are controlling that surface, and we have a tolerance of 0.04 with respect to A, B, and C. This is because we want to be able to ensure that this part would be able to slide between the inner walls of the outer case when the push button is actually pressed. And then we have a tolerance feature for 0.6 with a 0.1 upper limit and 0 for the lower limit, and these apply to the 2 holes with a true position tolerance feature with a tolerance of 0.05 at maximum material condition with respect to A, B, and C. This is so that we can line up the holes for the pin so that the latch itself can slide along within the slot and slide smoothly. And finally we have the 2 holes of 0.07 with an upper limit tolerance limit of 0.1 and a lower limit of 0, that with a depth of 0.2 inches. And what we're trying to control is the true position and the concentricity, and the tolerances are 0.1 and 0.2 respectively with respect to A, B, and C. This is just so that we can we can locate the pin that is coming from the push button itself, and it will be able to interface correctly with it.
Next, we have the SSD enclosure latch. This serves as the latch that slides into the hole of the storage compartment, which secures the entire mechanism. The main tolerancing feature here is the rectangular hole with a full fillet radius in the center of the part, which allows for the constrained sliding of the latch. A true position tolerance is used with a tolerance value of 0.01 to ensure that the hole will be aligned with the extruded circular boss from the storage compartment. An MMC modifier is used to denote and highlight the maximum tolerance at maximum material condition. In this case, since it is a hole, the MMC will be at a hole dimension of 0.03 with no bonus tolerance. As the hole gets wider up to 0.07, the bonus tolerance will be increased as well. The last component to feature is the SSD enclosure with the push button cap. This serves as the button that when pushed releases the latch as mentioned in the previous slide, allowing for the storage compartment to be removed from the housing. The feature has a true position tolerance with a tolerance of 0.04 since this feature will be directly connected to the latch toggle plate via two circular extruder bars. It is crucial to ensure appropriate tolerancing for this area. Another tolerance aspect is the perimeter wall of the button cap. A surface profile tolerance has been called out, highlighting a tolerance of 0.04. Since there is no additional modifiers, this means that the surface uniformity has to be within that constraint regardless of feature size. That is the end of the presentation. Thank you for listening.